then we use the remaining time to do revision. So today we discuss the last topic. Is just a quick or short topics on how to use ARMA, how to model, or we call it how to add or how to include the ARMA errors in the model regression model. Okay, so it's actually one of the possible way to improve the model in terms of the residual. Because remember that one of the assumption for the linear regression model requires the error term to be independent, or what we call serially uncorrelated. So for those who attended my applied course before, previous semester, so previously we discussed there are a number of different ways that we can use to remedy autocorrelation. So today we will discuss another possible way by using ARMA, by modeling ARMA, by modeling error using ARMA errors. Okay, we apply ARMA structure or ARMA model on the error term. So recall that in lecture 3, so we have regression modeling time trend, modeling trend by using regression, as well as modeling seasonal variation using regression as well. So that was discussed before. So we consider, for example, if we just for the case of model without seasonal variation, then we only have time trend. Okay, T time trend. So just regress the series, the time data against the time trend. So one assumption for the per model is that the error term is a White process, saying uncorrelated series. So if it does not, the model does not specify the assumption, so when you perform hypertesting, the result is not that reliable. Okay, so for example, let's include the seasonal variation test as well. So if you previously we just ignore the problem. So basically, previously when we perform the seasonal variation test, you notice that when we estimate the model, the mu was quite low, so it has autocorrelation problem in the residual. So it's not white noise. So basically, when we perform seasonal variation test, it's not that reliable. It's not that valid. So it's good that if you fix the problem first before you perform the test. Okay. So for your group assignment as well. So if trying to fix the problem when you perform your seasonal variation test, try to perform the test on a model that is we call it scientific model. Okay. So in this lecture, we consider fitting models where or whose error term exhibit autocorrelation. So the method we will adopt is to fit an ARMA process to the autocorrelated error term in the regression model. So for example, if the error term is in R1 model, then we can model the error term to be in. So basically, the first equation is the regression as well. I mean the model itself, the regression model itself, linear regression model. So we regress the seed time data against the time trend. But then the error term for that, the first equation is not certainly uncorrelated, it's really correlated. So you have to take into account that. So meaning that you need to take into account that the error term is not really uncorrelated, it's really correlated. So for example, in R1, then you have to model the error term to be in R1 process, and then you need to make sure that the second one, so basically the second error term for the second equation to be white noise. So where epsilon t is a white noise, but the ut, the residual or the error term for the first equation is not. So the general model for regression with ARMA errors is given by this equation. So we have the regression model, the first equation, and then the error term is not white noise, so that we model the error term using ARMA errors, the ARMA structure. Okay. So this one just like the ARMA model that we done before. So we can have uh, non-seasonal AR, seasonal AR, and then non-seasonal MPA as well as seasonal MPA. So consider an example. So we have data on annual motor vehicle production. So technically we don't have seasonal because it's annual data. For annual data, we don't normally seasonal variation occurs when we have seasons. So meaning that we have a number of observations per year. So it's not annual data. Definitely we don't have seasonal. Okay. But it seems that it has trend. So we can model as just like what we discussed before. Okay, so you can model. So this is data we have. You inspect the graph. Okay, and then we estimate model with trend. So we estimate what is usual. So just like before, we estimate equation. So we have ours. It is y space c for the segment space for the. So as mentioned before, you can either create a time trend variable first, like this. Or you can just use alternative way. When you estimate model, you can use the command like this. So you are. It's actually it's better to use this one because mentioned before, just like some of you had problem when you do your midterm test before. When you create time trend, but then when you estimate model, you put t, then it says there is not enough or sufficient data observation because for your t, you don't have value assigned for our sample. Okay, because when you generate series, when you generate series, you will generate series only for each sample, not only for it does not produce or assign value for the entire range. Okay, so that's why some of you before you're unable to estimate model. Because you don't have unable to estimate, unable to produce forecast because you don't have values assigned for our sample period. So it's easier to use this one because if you use this one, you don't have that problem now. Okay, if you use this one, you don't have that problem. Just add trend plus one. Okay. So trend is significant, deception is significant, but you see it was very low. So you record that. If you recall that what we discussed, we were did before that we were supposed to be around 2 to be a good model. Supposed to be around 2. If the value close to 0 or less than 2, substantially less than 2, so there is a positive autocorrelation. Okay, so we do have. So the error term it does not comply. The assumption of the error to be serially uncorrelated. So it is really serially correlated. So it is what was order. It is again. So we need to fix the problem in order to have reliable estimate of the error, reliable t-statistic, and as well, and then meaning that reliable p-value for hypothesis testing. Then you need to improve. You need to fix the problem. Okay, how to correlate the problem. So what we can do, either you use the technique, any of the technique that you learned before. Okay. In applying the cost, for example, but in this case, we will not discuss it. So in this one, we just use the method that we learned in the previous lecture. Okay, by adding ARMA error, so by modeling the error to be using ARMA structure or ARMA component. Okay, so this one, if you inspect the photogram, so you go to view. Residual diagnostic program for the residual program of the residual. So you can see it's not white percent. So residuals are not white noise. So it is really serially correlated. It's not really uncorrelated. So you have to fix the problem because it does not specify the assumption. The requirement for the error term to be white noise, so it's not white noise. So you have to do something. So in this case, what we can do, we can try to fix the problem by adding or by modeling, because the error is not really uncorrected. It's really corrected. You get this one. You get the choreogram. So in terms of pattern, it's just like the R1. The residual follows any R1 process. Okay, because this one spike at 1, cut off to 0. This one is going to decay. So we can improve our the model by providing more information to the model to tell that the error term for the regression model is R1. Okay. So you can estimate and just add R1. So now you see that you wasn't previously 0.5 something, now it's 1.63. So now it's getting closer to 2. And then, but this one only for first order, so you can check the program to spec for the IOS as well. Okay. So you check residual and a stick program again. Okay, so it's now, so just now we have about 25 plus square root of 5. So basically all greater than 1.5, so meaning that this model is now can be considered as the big. Okay, white noise can be considered as the error term, the residual can be considered as a serially uncorrelated. Okay, then you can use. So meaning that it's not sample. If you want to make inference, for example, on the significance of the trend. Okay, there is trend now, of course, there is a significant trend. And then you can use model to produce forecast. So to produce forecast, you can just produce forecast as usual. So you go to forecast, and then you can just put the name for the forecast series. If you want to calculate forecast intervals, then you can save the SE as well. And then forecast sample. Let's say you want to do forecast for the next 3 years, starting from 1990 to 1992. Okay. So forecast value are given here for the last 3. Okay. So if you want to calculate manually, then you should write the equation first. Okay. So if you want to use So if you want to calculate manually, then you have to derive the forecast equation. So you write the equation, you have 2 equations, and then you combine the 2 equations to be 1 equation. So meaning at this part, you rewrite this one and then you plug into the first equation, and then you get this one. And then from here, if for one step 8 you plus 1, then everything plus 1. Okay, and then from there you can calculate. So you can get the value of. So C in use give us this one. Okay, and then the AR1 give us estimate for V1. Okay, estimate for V1. So later an example example of calculation for this model. So for 2 step 8, everything plus 2. For 3 step 8, everything plus 3. So later you have time, you can try to calculate But if we calculate manually, then possible that you get slightly different, slightly different test lah. Okay, so because of decimal place, so the numbers it is rounded to a certain number of decimal places. So when we calculate, it's slightly different to the one that given or produced by use. Okay, now you also can add regressors in the model, but the problem with this kind of model, so previously all the models we discussed before, we only have what we only use what we call as univariate model. So the benefit of using univariate model like exponential smoothing, then we have what we call as ETS. We use regression, but we only regress against time trend instead of variation, and then alpha without regressors. So the benefit of using univariate model like that, or the T model, which can be considered as univariate model, it makes it easy for us to produce forecast future value and forecast of future value. Although you can include regressor in the model like this, but whenever we include regressors, it's not really useful for the purpose of future forecast. Okay, because for example, you want to do forecast of sales, you model the sales against, you regress model against other regressors. Okay, let's say income, for example, family income or whatever lah, for example, and other variables. So if you want to do, whenever you want to do forecast, you need to know the value of X as well. So it's not really makes sense. In a real or actual practice, or a real practice. So if you want to use forecast of the future value of this series, but you do not know the value of X, the future value of X, so it's not really useful, right? Okay. So that's why in previous weeks we discussed on the use of univariate models. You can add the previous information, the past historical information of the same series in terms of trend, in terms of seasonal. Okay, and then we use that information to do forecast for the future. But univariate model is only useful for the case of series that has strong or obvious trend and seasonal variation. So if the series is what we call as affected or very heavily influenced by other factors, then it's not really useful. I mean, you can use, but for long-term forecast, it will not produce good forecast. Okay, although you can, but you cannot expect that model to produce very good or accurate forecast for many step ahead forecast. So when the series, let's say for example, you have stock price data, the stock price value is actually affected by many factors. So it does not have clear trend, clear seasonal variation. So if you apply the normal or univariate model, exponential smoothing model, for example, or ATS, and then ARIMA without regressors, then although you can get forecast for short term or long term, I don't think quite unlikely. It's quite unlikely to get a good forecast. So for the series that is affected by other factors, then you have other variable. You need to explain that using other determinants okay, the influencing factors. But the problem with this kind of model, actually about this now, the problem with this kind of model is actually useful. The regression model is useful for us to identify or to investigate the factors affecting the dependent variable. But for the purpose of forecasting of future value, is not really useful. Because why? Because we need to know all these value of X before you are able to calculate prediction or forecast for the dependent variable. Okay. However, if let's say in a certain situation, you are able to have a good estimate of X regressors, and then you can use that. Let's say there is a variable that you can get someone, an expert, for example, to advise what is the possible potential value of X for the next month, for the next 2 months, for the next 3 months. And then in that case you can use this kind of model. Yeah. you want to use regression model like this. So where yt is a linear function of the key predictors variable. So we have a set of independent variables x1, x2, xk, and the epsilon t is usually assumed to be, so the error term assumed to be an uncorrelated error term. So it is a white noise. So tests such as the Jungbox test can be used for assessing whether the resulting residual was serially correlated. So it's one straightforward. So when it is to be serially uncorrelated, so you can check the hologram and also perform the Jungbox test in order to conclude whether residual of this regression model is serially correlated or serially uncorrelated. So if it is really uncorrelated, it is serially correlated, then you have to fix the problem just like before. So here we allow the errors from regression to contain autocorrelation. To emphasize this change in perspective, we will replace epsilon t in the first equation, this one, with ut in the equation, and then the error series ut is assumed to follow an arima model. So for example, if ut follows arima 111, we can write the equation to be like this. So meaning that we have a regression model, so dependent variable y, and then we have a set of independent variables x1, x2, x3 up to xk, and then we have an error term. But error term is not really uncorrelated. It's not really uncorrelated. It's really correlated. Then you can model the error term using arima. Okay, and then because arima errors lah. So by this one, epsilon t must be a white noise series. And then notice that the model has two error terms here. The error from the regression model, which we denote by the mu t, and the error term. So this one, okay, so we use different symbols. So you also can use other symbols if you want to avoid confusion between mean and the error. Then you can use different. You can choose to use different symbols. Okay, and the error from the arima model, which we denote by epsilon t, only the arima model errors are assumed to be white noise. So this one, we need only this one. It must be a white noise, but this one it is okay to be not to be white noise. So that, but we can model. Okay, we can model the error term proposed equation using arima errors. So an important consideration when estimating a regression with arima error is that all variables in the model must first be stationary, because if you have other variables in the model, so previously we only have time trend. So previously when we construct model, we only have time trend, and then it's fine, because there is no possibility to have what we call space regression. But if you regress y times delta against other times delta, then you have to be more careful. Okay. So an important consideration when estimating the regression with arima error is that all variables in the model must first be stationary. That we first have to check that yt and all predictors, all the independent variables x1, x2 up to the last one appear to be stationary. If we estimate the model when any of these are non-stationary, the estimated coefficient will not be consistent estimate and therefore may not be meaningful. So if your data is not stationary, you regress against other non-stationary data, then in terms of hypothesis, so it is not that reliable. It's not reliable for you to make conclusion whether any of x is significantly influenced the dependent variable y. Okay, because the error term, the residual is not white noise. So there is when the model suffer autocorrelation problem, it has influence or its influence on the reliability of the estimate for the static error. Okay, this estimate is relatively valuable as well. So if we estimate the model when any of these are non-stationary, the estimated coefficient will not be consistent. Okay, this one I specified just now, and therefore may not be meaningful. One exception to this is the case where non-stationary variables are co-integrated if there exists a linear combination of the non-stationary yt and the parameters, then that is stationary, then the exponential coefficient will be consistent. So if y and x are co-integrated, then okay lah, you can regress even though they are not stationary. Okay. So if we therefore first difference the non-stationary variable in the model, if let's say they are not co-integrated lah. Okay, if they are not co-integrated, then you have to different the series first. Okay, so it is often desirable to maintain the form of the relationship between yt and the parameters, and consequently it is common to difference all of the variables if any of them need differencing. So let's say you perform your test on all the variables, dependent variable as well as independent variable. Some of them I1, so meaning that requires one differencing in order to make it to be stationary, but some of I0 meaning that it's already stationary. Okay, so although you need to, in order to, you actually require the series that is not stationary to be stationary by applying differencing to that variable only. However, as mentioned here, so we can choose to, if let's say some of the variable is already stationary, so you can just apply differencing to all, so that you can preserve the same what we call that form of relationship with variable. Where this one? Okay, this one. So let's say you perform your test, but not all. Some of the variables not stationary, but it's not stationary, but other variables, some variables are already stationary at levels. Okay, although you can just apply differencing on the non-stationary series, but as is mentioned here, it's a common that we want to. It's often that we want to maintain the same form of relationship between y and parameters, so that what we can do is we can choose to apply differencing to all variables, even though some of them already stationary, so that in terms of integration, then easier, so that you can say that you can interpret as the changes in the variable, the impact of the changes in y per unit changes in each of x. If you only apply differencing to non-stationary series, so meaning that you have a mixture, you don't have the same form of relationship between variable, because some using level, some variable you use the first different, so it's not consistent. Okay, so it's okay that you apply differencing to series that is already stationary in order to maintain the form of relationship between variable. Okay. So the resulting model is then called a model in differences as distinct from model in level, which is what is obtained when the original data are used without differencing. So now consider another example. So we have the data on oil price, and we also have some oil. So basically, two are related. So the price of oil, although it's not totally dependent on the price of sunflower oil, but it is actually affected by it, because normally they are working together. So when the price of sunflower oil, because the sunflower oil is substitute product, substitute item for the palm oil, cooking oil. So when the sunflower oil increase the price, it also will increase the price of the palm oil as well. When the price of sunflower oil reduce, it will have some, to some extent it will reduce the price of palm oil as well. So basically they are related, but if you look at to the graph, basically in terms of the distance, the way or the magnitude of influence is not always the same. Okay, you can see here the distance between the two quite large as compared to this. Okay, this one the distance quite small. So if you investigate whether the one is greater or not, actually the result says that we don't have enough information. So if you got that how to know whether the variable are integrated, you can use RDL, for example. So the data given here. So we have okay, so this one the data, this is now how to produce the graph. If you open as a group like this, you highlight the two, and then you open as a group. Okay, and then you can just go view and then graph. View graph. So to get the graph, the same graph that given in the page. So you can see that, actually you can see in terms of the distance. Basically we know that they are connected to some extent. Okay, to some extent, if the price of sunflower oil influence the price of, but it's not the only factors. It's not the only factor affecting or determining the price of the palm oil. So if you for example, if you run the bound test, for example, we estimate model. This one is covered in my applied. Other applied because we learned before. I just showed that. Don't worry lah. You haven't learned it. Okay. Just want to show you how we are able to know whether the variables are integrated or not. You can one of the available method is the bound test lah. Okay. So if we regress CPO against sunflower. And then use RDL, for example. This one I showed it again. So you go to quick estimate equation. This one for those who learned it before, it will not be covered. I will not ask the same thing. This topic in the exam because you do not learn this in this course. Okay, it's covered by other course. So it will regress the CPO palm oil price again sunflower oil price, and then we use RDL, for example. And then just OK, and then you go to RDL diagnostic, the bound test. RDL diagnostic, the bound test. So you see the test statistic 3.3, and then the critical value 5%. So meaning that it is less than. So it is considered as not integrated. Okay, so they are not. They are related, but in this case, because of the I mentioned just now, the distance is not consistent. So it's considered to be not co-integrated. So if you still want to regress CPO against sunflower, and then what you need to do, first check whether they are stationary or not. If you check, you perform universal test, it turns out that the two variables are not stationary, so they are not integrated based on the bound test. So you have to apply differencing. Okay, you have to apply differencing before you regress. Okay. So now you perform the universal test, whether in order to identify whether the two variables are co-integrated or not, the two variables are stationary or not. So we perform the test as usual. AEF test, for example. So CPO. So this is our independent variable. So perform the unit root test. Standard unit root test. test using second equation intercept. So if they say out of 3 equations I mentioned before, if you want to perform the test, at least perform the test using the second equation intercept. Okay. If you just want to perform the test using one equation, but it's better to perform the test using all the equations, so that you can have more information to make a better decision. So this one, if they say, you perform this one for this example, for this data, you perform the test using all the equation, the result or decision is the same. Or for example, if level intercept, so the level is non-stationary because p-value greater than 0.05. Okay. You perform the test using other equation also the same, it produces the same result. The none, for example, also the same, greater than 0.05. But this one, you look at the graph, doesn't seem to have deterministic trend. This one, even this one not significant. So quite likely that you have to use the third equation. Okay, just now when you see the graph, it doesn't seem to have deterministic trend. Okay, so but even if you use all 3 equations, it suggests that level is not stationary. Okay, and then if after you apply first difference, so whether it is stationary or not. Okay, perform the test again on the first difference. Okay, so it's now the first difference is stationary based on the second equation. If you perform the test using other equation also the same, trend itself also the same. So in that it is I1 integrator of the 1, and then you do the same for the other variable, second variable, sunflower. You do the same. Basically, the result also the similar. So this one also I1. So level intercept, so it is greater than 0.05 if you apply differencing to first order difference, the non-seasonal difference, the first order of course difference. So is it now such? So in this case, if you want to regress CPO against the sunflower, then you have to apply. You have to regress the first difference. Okay, the first difference of the CPO against the first difference of the sunflower. So now you estimate the model. Quick estimate equation. So we have first difference of CPO. Okay. So so now we have this result, but C is not significant, so you can so basically C is up to you, optional whether normally in regression we keep the C, okay, but you actually can take out as the alpha model, for example, normally it's not significant, we take out, so it's easier for us to write the equation. Okay. So so if we remove C, well, because it's not significant, so we get this, and then you notice that it was some 1.52, so it's not so unclear whether residual or not or not, so you check the polygraph. Okay, you go to view residual program to state. So you can see here. So we have just now we have about 100 something. So this one you can see that less than 0.05. So it's not. It is not adequate model. So you can improve the model, or you can improve model by adding RMIRs. So in this case, we consider this as exponential decay. This one as the first spike at 1 cut off to 0. So you can try to add anyone. Okay, estimate anyone. Okay, so now you have the person 2.06, and then you check again residual program. So now we can consider model is an adequate model, and you can now it is more reliable to make conclusion about the significance of the influence of sunflower oil price, okay, on the CPO price. Okay, in terms of this P value, it is significantly influence. Okay, but less than 5%. So to write the equation, you can write like this. You refer to the additional note given. This one. How to write the equation. So this one, the previous one, this one, the one that we discussed last week. Sorry, this one, regression with RMS. Okay, so this one, as the example, the first example, when meaning that you only have trend, you have seasonal dummies. So if you have trend, if you have seasonal dummy, then you have to include seasonal dummy as well. So the example, the first example, example one, you only have trend. But if let's say the series has seasonal variation, then you have to include seasonal dummy as well. Okay. So we have example later on, exactly the same model like this. So we do that later. For model regression, you need to use this equation. So you have differencing of the variables, dependent and independent variables. So normally we apply the same in order to maintain the same form of relationship. We apply the same order of differencing. So you apply differencing on any other variable, then we apply the same on all variables. And then the other term follow RMIRs. So you can write equation like this, and then you combine, and then you combine to be one equation. And then using this one equation, you can produce forecast. Okay, you can derive forecast equation. If everything plus one, you have the forecast equation for one step A forecast. For two step A forecast, you got everything plus two and so on. So this one, if you want to produce forecast, and then you can just by this one. Okay, this one the problem is model actually for now because you have regressor. If you want to produce forecast for out sample period, then you need to be able, you need to know, you need to have a good estimate of the regressor. Okay, otherwise it's not really useful the model. Okay. So although you can forecast using one possible way, you forecast some problem using univariate model first, for example, and then but you can try whether it produce good. Well, for your group assignment, I think you can just use this one. I mean, for your group assignment, you just use this model, trend and signal variation without regressors. Okay, without regressors. This one just this it's possible to include regressors as well, but in terms of the usefulness of the model for purpose of forecasting. For the purpose of forecasting, it's not really useful. If they say your model, you have the current value of the regressors explaining the current value of the dependent variable. Okay. However, you have, if let's say you are able, let's say the dependent variable is influenced by the previous or past values of the regressors, and then you can use lag operators. Okay, so instead of using the current value of x to explain the current value of y, if let's say you have daily data for example, so daily data of sales of certain product, and then you have the price of other substitute product, daily price. So perhaps when the price of other product drop, then the influence of the sale, the influence of that, the drop of the price of the substitute product take place in the next few days, for example, in the next few days, and then you can use that. Okay. So you can use, for example, lag 1, lag 2. So the last few days, for example, the last few days of the regressors. So in this case, you can produce forecast, but it's not only for the next few. Only it depends on how many lag you have. Let's say if you want to produce forecast for one step in forecast, then you don't have this one. For example, if you exclude the current value, you only have lag 1. Then you can produce forecast up to one step in forecast using the data or the previous value of the x. Okay, if they say the x, let's say you have daily data, so the data for the last 7 days, has significant influence on the data of dependent variable for a time t, and then maybe there you can produce forecast up 7 step 8 forecast. Okay, 1 step 8, 2 step 8, 3 step until 7. So it depends on how you construct your model. It depends also suitability lah. I think quite unlikely to have that kind of data. I mean, normally what happen? If daily, okay lah. If you have monthly data, for example, it's quite unlikely the data for few previous months influence the data for the current months. Although it's possible lah, it's possible to use the reason. So it depends. Okay, it's possible for you to use, but whether the data is suitable or not to be used for that particular data. Okay. Alright, so we do the last lab session 10. So as a summary lah, so previously when you learn regression, econometry, especially econometry is mostly used to estimate the significance of influence. So meaning that you want to identify what are the factors that significantly influence the dependent variable. So that's the main use of regression model or econometric model. So the time series model, like what we discussed in this course, the use of ARIMA model, ATS, exponential smoothing model, that is actually the main purpose of that model is forecasting. So individual regression is quite difficult to make the forecast of the future value, because we need to know the value of the regressor as well. So given here data on number of tourist arrival in Malaysia, this one total, it's not for any particular country. Total number. For 7 years, so below plot of ACM and PCM by the series. So describe the characteristic of time series plot and explain what should be done for the series to be achieved stability. So basically, you have data, then you can perform you can perform the relevant test. For example, the unit test in order to identify if it is stationary or not. If not stationary, you have to apply different thing. And then you also check whether it has an variation or not, using, for example, by conducting seasonal variation test. So but in this case, you don't have the data, yet you only have this information. And then what you can do is inspect the graph. Inspect the graph, of course, you can see it does not specify the condition for the series to be stationary, which requires the mean to be stable. Definitely mean not stable because this one is split into two. The average, the mean for the series, for the first part here, second part here, so it's not stable. So based on the graph, we are able to see that it's actually not stationary. And then by looking at the program, at leg 12 because monthly data, so monthly data, if quarterly data, you inspect at leg 4, 8, 12 and so on. So this one monthly data, you inspect at leg 12, 24, 36. So you can see at leg 24, at leg 12, you can see the sample auto correlation higher than as compared to at leg 11, 13 and the other nearby sample auto correlation. So it indicates the reason of seasonal variation. So in order to apply our model, so you need to apply different signal. Although it is acceptable, okay, to apply non-seasonal difference, but as what I explained before, if we have seasonal variation and the series is not stationary, then we are advised, we are encouraged to apply seasonal difference first, okay, as compared to non-seasonal difference. Although it's okay, it is acceptable. Even in reviews later on, if you notice that, okay, later we show you that reviews also has what we call as automatic model selection for the ARIMA model, but reviews only consider non-seasonal difference. So that's why when we perform the numeric test, it only has option for the first difference, second difference. It does not provide the result for the seasonal difference. So in order to perform the test on the seasonal differences, we have to generate our own seasonal differences. So this one, based on the graph, so we have data here. So data. So if you inspect the graph of data, so again, this one you can see. Of course, you can perform unit test. Based on unit test, you will find that it's not stationary. Okay, you perform the test. Okay, this one unit test. For example, level intercept. Okay, this one. Okay, now this one, based on the second equation constant, it is p value greater than 0.05. But if you perform the test using the third equation, trend intercept. Now the result says that there is no linear root. Different. Why? Because it has deterministic trend. So this one, you see that it has deterministic. So it's actually trend stationary. If you compare AIC and SIC, this one has smaller AIC and SIC. This one, the third equation. So you need to be careful. So if your objective you want to construct ARIMA model, for example, then you have to apply different thing because it has deterministic trend, even though there is no linear root. Okay, it has. So this is what we call as trend stationary. Okay, so I think you understand. So in this case, the second equation, the first equation, second equation suggests the series is not stationary. Okay, there is a linear root, but the third equation says that there is no linear root. Okay, but it has trend. It has deterministic trend. So in this is better than you should apply different thing. If your objective you want to construct a model. So if not, if you just want to construct a regression model, then you can just add time trend in the model. Regression, you just regress y and give the time trend and okay lah. You don't need to apply different thing in that case. Okay, but in this case, because you want to construct a model, then you have to make a series stationary. Okay, so what we need to do, the series is not stationary, and then you get the quadrant. I mean, you see that the value higher for the leg 12 compared to the other nearby. So it suggests presence of seasonal variation. So we perform seasonal difference. So let's say after you apply seasonal difference, and then you perform the test again, and then you conclude. So this one, so in use how to, we don't have, in order to check or perform the unit test again, we don't have option for the seasonal difference series. We do only have first difference, second difference. So in order, if let's say you apply seasonal difference, then you have to create your own. You have to create the variable the series, the seasonal difference series. Okay, so you go to quick generate series, and then we have we name the series to be seasonal difference of y as dy. This one is up to you. You want to use different names, okay. Okay, as dy d bracket y comma 0 comma 12 because it's multi-later. Okay. So now to perform the unit test on the different series, then you have to check. You have to perform the test here. Okay, you have to perform the test on the seasonally different series. Okay, so you go to view. You do test in the app, but this one you select level before you perform the test on this series level. And then they say the cell and this is the cell. Okay, you do both lah. In the set at least this one and it's equals to. Okay, so now based on the second equation, it is stationary. The third equation is stationary as well. Okay, so it is meaning that you need to apply for the difference. So now you can identify potential model by looking at the colograms of the seasonally different series. So you go to view, time series diagnostic cologram of the level because this one level of this seasonal different series. Okay, and then you can identify the possible model. So this one question B, inspect or estimate the result of the test for the different series, and then choose model in between model 1, model 2. So this one, what I can propose. So if you look at this one, if you consider this as function decay, this one spike at 1 out to 0, then it R1. Okay, R1 or MA5, but MA5, I mean, if you compare to if this one select 1, then normally we go for R1 because less number of parameters. Because in MA5 we have 5. Okay, R1 is only 1. The parameter to the estimator. If you want to explore, you can, if you say you want to compare your IC, which one is better, then you can try to move. But in this case, if you just want to, if let's say question like this, for example, I suggest, ask you to suggest one model, then you just suggest R1. Okay. The R1, considering that it's such decay, this one, spike 1 to 0, and then you can estimate the model now. Go to quick estimate equation. Okay, so we have D. Do not put SDY because later on you cannot produce forecast for levels. If you put SDY, then later you can only produce forecast for the different series. But we want to produce forecast for the levels. So we have to put D Y0 space 12. Okay. So remember, your assignment do not put SDY if you have significant, because your forecast actually produce forecast for the different series. Not forecast for, so MAPE, when you calculate MAPE and so on, it is actually MAPE for the forecast of the different series. Okay. So when you write your model, put this one. Okay. Dependent variable D bracket the different series of D. This one is the different series. Okay. I think in the past some students they put apply different thing and then put as the difference in the model. For example, this one you create SDY. Some students previously they put as SDY as the variable, but when you do that, it produce forecast for the different series, not for the levels. Okay. So we have C and then the R1. So recall that I explained last week, certain software like R, when you apply differencing, then you will only consider model with zero mean. But it does not happen in use. You put C, you use. I mean, you can have even in R also you can specify if you want to have you want to allow the model to have non-zero mean, then you can what we call that, you need to write now. If you put exclude mean, you need to put true, something like that now. Okay, instead of the default one is actually false, mean and without trend, without mean. Okay, but if you put C and it's significant and you retain it, so meaning that you have the model with non-zero mean now. Okay, even though you apply differencing. So in R1, so C significant, so meaning that the seasonal difference series actually has non-zero mean. Okay, it is stationary, but it has non-zero mean. So you have to use just like YT minus mu in the equation, so that you have the non-zero mean. So this model adequate or not? You can check just like before lah. You check the Harman structure for the stationarity. It is stationary, and then residual. So it is adequate model. P value. I mean this one because you have certain value, you have less than 0.05, so you have to perform a trend. So you have to identify included observation just now. When you estimate, you have about 72 square root of 72. About 8 something. So you can perform the test, the reduced pop test at 8 for example. So its P value greater than 0.05. So you conclude the residuals produced by the model are serially uncorrected or unprocessed. The model is inadequate, then you can use the model to produce forecast. So if you compare, you look at the question, we have another alternative model. Model 2, this one model 1, the model that we estimated just now. Model 2 without C, and then you can see the model is not liquid. Okay, if you inspect the model without C, the residual, hologram of residual, you can see that it is considered to be not liquid, a white noise. It's not white noise. Residual not white noise because less than 5%. So in between the two models, then we should use model 1. Model is constant. Okay, with R1 with non-zero mean. So write the final model that you have selected in part P in terms of the Bankshire operator and without the Bankshire operator. Relax operator, then write the fitted model based on the estimation result given in part B. So how to write the equation? You need to refer to the actual the equation for Riemann individuals. Do not use simplified equation. Do not use simplified equation given in the lecture note, because remember we have differencing plus non-zero mean. Then you have to refer to use the actual equation. Riemann individuals. So you have to write the equation, the model into the equation like this. Okay, and then you combine them. So you combine the two, just like before. So meaning that you bring this to this side. So you have mu t equal epsilon t over this, and then you put here, and then you expand in this one. Okay. So from here, and then you can determine your forecast, fitted equation as well as forecast equation. So this one C gives you estimate for mean, and then R introduced just now. Okay, this one gives you the estimate for P. Okay, and then you can to compute forecast, then you can just identify. So you are given a table that is something like this. And from here you have your determine your forecast equation. So you then identify. So if one step in forecast, everything is +1, and then you identify what is the value of yt. The last value of y is sample is 100 yt, and then yt minus 11. Okay, yt minus 11. So you count. So -1, -2, -3, -4, 5, 6, 7, 8, 9, 10, 11. So yt minus 11 is 1. Okay. And then yt minus 12, the next one, the one before that. This one. Then you calculate. And do the same for two-step in forecast. So everything +2. So in abuse, you just do to forecast and then increase forecast as the slide before. YF. Okay, you want to calculate forecast table, you say rest it. But this one we just want to calculate forecast. So YF 2012 January 2012 February 02. Okay. So you have the forecast value given here. Last two. 2050 something, 179. So this one, one step in 2050 something. And this one. Okay, the next question. Now we consider an alternative model, regression with Riemann errors. This one. So the following table give estimated coefficient for two linear regression model. So Y denote the number of variables, it is, and then T is time trend, and then D is the dynamics. Okay. So now we want to use a regression model. Okay, this one I close first. So the same data. So just now when we inspect the graph, so we see it has trend, and then when we inspect the variation, it has a variation. So if we want to construct a regression model, yeah, then you learn in lecture 3, and then we can estimate a model like this. So quick estimate equation. So we have Y, the tourist arrival data, and then we have C, trend, and then seasonal variation. Okay, this one, let's say we want to include all dummy variables, then we have to take out C lah. Okay. So expand minus advance. Okay. So we get estimate. But you see that it wasn't quite close, 07.02, and then when you inspect the residual, program or residual, you see that it's not wide enough. So one way to improve the model is by modeling the error to be using ARMA structure. Okay, so you consider this one. The first few lines you can see that. So I like. Okay, although you can try to include the version as well, but you can try to include the non-seasonal ARME first. So this one, just like R1, okay, just like R1. So you can estimate and add R1. So we just want to have the residual to be white noise. So we need to, in order to have a valid model, we need to improve or make sure the residual to be white noise. now equipped. So the next question, produce forecast for December, for the January and February, given data for December. Okay, so this one to produce forecast, you can do the same. Okay, so you put the forecast and then YF model 2 for example, and then so we have 2012 January, 2012 February 02. Okay, so your forecast values given here. So now you can compare. So model 1, model 2, the first method, Alma model. Second one is regression Alma error. So you can compare which one. If you compare in terms of MVP, which one is better? Yeah. So so you know the explanation of model 2 is better because it is an equipped model. To write the fitted equation is actually exactly the same to this model. Okay, so this model we have example given here. So we regress against trend and then seasonal variation, and then we have R1 for the error term. Okay, and then you combine the two equations to be like this. So this one you rewrite this one second equation and then you put into the first equation, and then you have only one equation. Okay, and then from there you can determine your forecast equation. Okay, forecast equation. So one step ahead forecast, everything plus 1, 2 step ahead, everything plus 2, and so on. So this one is simplified equation because this one, seasonal dummies, here seasonal dummies, because we know that for each of observation, there is only one dummy that equals 1. Okay, for example, for January, only D1 equals 1. For February, only 2 equals 1, so we can simplify the equation. But if you want to write the fitted equation, the estimated model, then you have to write in full. So you have to put gamma 1 D1 plus gamma 2 D2 plus gamma D3 and so on. Okay. So this one simplified equation because for each observation, there is only one dummy equals 1. Because that observation cannot belong to 2 seasons, cannot belong to 3 seasons, it only belong to 1 season. Okay, meaning that for each observation, only one D, D1 dummy variable, D1, D2, D3 and so on. Only one dummy variable, seasonal dummy variable can only equal to 1. So basically this is a simplified equation. Okay, if you want to write the fitted equation, then you have to write the equation in full. For example like this, you have to put all. Okay, for D1, D2, D3, D4 and D12. Okay, and then for this one for the same, the same, but you just write the complete equation. So to produce forecast from here, you identify. So if for the January, then you take value for January. But for this one for January, because we have the equation says that the coefficient of the dummy for January. But here in this part, because T, this one T plus 1, so because forecast for T plus 1, this one is the same one. But this one T means that the previous one. Because if this is the forecast for January, so this is the coefficient of the dummy for January. But here T, this one T plus 1, so T means that the previous one. So meaning that coefficient of the dummy for December, the previous one. Okay, so you have to use value for the December for this one. Okay, so later try to calculate so that you understand how it is calculated. So February also the same. Okay, so based on this you calculate. So just now, okay, this one 2194. This one and then 2085. Okay. So we have discussed everything, all lecture, all topic as well as lecturation. So after break we discuss the answers for the midterm test. You want to discuss or not? Answers for the midterm test. If you want to discuss after break, we discuss. Okay. After break we discuss. So then you know I have marked your answers. From our relation should we should be able to expect what one you can get. Okay. So after break, so half an hour break, so we continue.